Our first learning algorithm will be linear regression. In this video, you see what the model looks like, and more importantly, you also see what the overall process of supervised learning looks like. Let's use our motivating example of predicting housing prices. We're going to use a data set of housing prices from the city of Portland, Oregon, and here I'm going to plot my data set of a number of houses that were of different sizes that were sold for a range of different prices. Let's say that given this data set, you have a friend that's trying to sell a house, and let's say your friend's house is of size 1,250 square feet, and you want to tell them how much they might be able to sell the house for. Well, what you could do is fit a model, maybe fit a straight line to this data. That might look something like that. And based on that, maybe you could tell your friend that looks like they can maybe sell the house for around $220,000. So this is an example of a supervised learning algorithm, and it's supervised learning because we're given the quote right answer for each of our examples. Namely, we're told what was the actual house, what was the actual price that each of the houses in our data set was sold for. And moreover, this is an example of a regression problem where the term regression refers to the fact that we're predicting a real value output, namely the price. And just to remind you, the other most common type of supervised learning problem is called a classification problem, where we predict discrete values outputs, such as if we are looking at cancer tumors and trying to decide if a tumor is malignant or benign. So there's a 0-1 value discrete output. More formally, in supervised learning, we have a data set, and this data set is called a training set. So for a housing price example, we have a training set of different housing prices, and our job is to learn from this data how to predict the prices of the houses. Let's define some notation that we're using throughout this course. I'm going to define quite a lot of symbols. It's okay if you don't remember all the symbols right now, but as the course progresses, it'll be useful to have a convenient notation. So I'm going to use lowercase m throughout this course to denote the number of training examples. So in this data set, if I have, let's say 47 rows in this table, then I have 47 training examples, and m equals 47. I'm going to use lowercase x to denote the input variables, often also called the features. So that'll be x's here, would be our input features. And I'm going to use y to denote my output variables, or the target variable which I'm trying to predict. And so that's this second column here. A little bit more notation. I'm going to use x comma y to denote a single training example. So a single row in this table corresponds to a single training example. And to refer to a specific training example, I'm going to use this notation xi comma yi, and going to use this to refer to the ith training example. Right? So this superscript I over here, this is not exponentiation, right? This xiyi, the superscript I in parentheses, that's just an index into my training set, and it refers to the ith row in this table. Okay, so this is not x to the power of I, y to the power of I. Instead, xiyi just refers to the ith row of this table. So, for example, x1, refers to the input value from the first training example. So that's 2104, right? Because that's x in the first row. x2 will be equal to 1416, right? That's the second x, and y1 will be equal to 460, because that's the y value for my first training example. That's what that 1 refers to. So as mentioned, occasionally I'll ask you a question to let you check your own understanding. In a few seconds in this video, a multiple choice question will pop up in the video. When it does, please use your mouse to select what you think is the right answer. We've defined what a training set is, and so here's how a supervised learning algorithm works. We started with a training set, like our training set of housing prices, and we feed that to our learning algorithm. It's the job of a learning algorithm to then output a function which by convention is usually denoted lowercase h, and h stands for hypothesis. And what the job of the hypothesis is a function that takes as input the size of a house, like maybe the size of a new house that your friend is trying to sell, so it takes in a new value of x, and it tries to output the estimated value of y for the corresponding house. So h is a function that maps from x's to y's. People often ask me, why is this function called a hypothesis? Some of you may know the meaning of the term hypothesis from the dictionary or from science or whatever. It turns out that in machine learning, this is a name that was used in the early days of machine learning, and it kind of stuck. It's maybe not a great name for this sort of function for mapping from sizes of houses to the predictions, but I think the term hypothesis maybe isn't the best possible name for this, but it's the standard terminology that people use in machine learning now. So don't worry too much about why people call it that. When designing a learning algorithm, the next thing we need to decide is how do we represent this hypothesis h? For this and the next few videos, I'm going to choose our initial choice for representing the hypothesis will be the following. I'm going to represent h as follows. I'm going to write this h subscript theta of x equals theta 0 plus theta 1 of x. And as a shorthand, sometimes instead of writing h subscript theta of x, sometimes as a shorthand I'll just write this as h of x, but more often I'll write it as a subscript theta over there. And plotting this in pictures, all this means is that we are going to predict that y is a linear function of x. Right? So that's our data set. And what this function is doing is it's predicting that y is some straight line function of x. That's h of x equals theta 0 plus theta 1 x. Okay? And why a linear function? Well, sometimes we'll want to fit more complicated, perhaps nonlinear functions as well. But since this linear case is the simpler building block, we'll start with this example first of fitting linear functions, and we'll build on this to eventually have more complex models and more complex learning algorithms. Let me also give this particular model a name. This model is called linear regression, or this particular example is actually linear regression with one variable, with the variable being x. Right? So predicting housing prices is a function of the one variable x. And another name for this model is univariate linear regression. And univariate is just a fancy way of saying one variable. So that's linear regression. In the next video, we'll start to talk about just how to go about implementing this model.